Yeah, thank you very much for the introduction again. Okay, I hope I'm audible. All right, so just like yesterday, I'll try to do this on these slides. Let's see how that goes. Okay, so yesterday we saw a definition of Hilbert modular forms, and I stopped with the notion of Q expansion or Fourier expansion of Hilbert modular forms. Okay, so let's recall a little bit what a Hilbert modular form is. So Hilbert modular form of level B is an integral ideal. Weight K is a tuple of functions. So how many functions do you have? You have the cardinality of narrow ray class group, that many functions, from d copies of the upper half plane to complex numbers. These are holomorphic functions, and they satisfy this modularity property. Okay, so if you like, you can just think about usual modular forms for now. And conceptually, whatever I'm going to do is more or less sort of same level of depth as what you would do for modular forms. So you can just think about modular forms. This is just more technical, more notations, and at times sort of slightly conceptually deeper because of various issues like the class number, narrow class number of the field may not be 1, etc. Okay, and then the modularity property, just like for modular forms, it gives you a Q expansion, Fourier expansion. And in this, so you saw Fourier expansion of the elliptic modular forms in Schoenach's talk. They were, as we said, they were, as I said yesterday, they are indexed by non-negative integers. In this case, they are indexed by, so remember we had fixed this integral ideal T lambda representing class lambda in the narrow ray class, class group of F, and the Fourier expansion are indexed by Fourier expansion of F lambda are indexed by totally positive elements in T lambda and 0. Okay, so these are what are called non-normalized Fourier coefficient, and to normalize them, we just do this. Okay, so these are more canonical things. These are the things that will turn out to be Hecke eigenvalues of normalized Hecke eigenforms. Okay, the normalized Fourier coefficient. So the second lecture begins with examples of Hilbert modular forms. So yesterday we did not see examples, and the most, I mean, for us the most important example is that of Eisenstein series. Okay, and these are the modular forms that you can write explicitly. Okay, so these and theta series are basically the only modular forms that you can write explicitly. And so let me introduce them. I'll give you the Fourier expansion, the normalized Fourier expansion explicitly. If you want to read about this, then a reference for this is a Duke paper of Shimura. I forget what the exact title is. And another reference is, so for the precise thing that I am going to talk today and tomorrow, my paper with Shamit Dasgupta on constant terms of Eisenstein series. So this is on the archive, for example. Okay, but we basically make whatever Shimura has explicit in the cases that we need it. So the basic reference for all this is Shimura's paper, and it's kind of daunting as most things that Shimura writes, but it's all very explicit, and if you spend enough time with it, it's not hard to understand. Okay. So to define an Eisenstein series, what do I need? I need to, as with rational numbers, you need a pair of characters, and then you can define the Eisenstein series attached to those pair of characters like this. Okay. So this is what we are going to do. We take characters eta and psi modulo a and b. Okay, so these characters these need not be primitive characters. So their conductor could be a strict divisor of A and B. So that's why I write modulo A and modulo B rather than of conductor A and of conductor B. Each character of the totally real number field F that we had, it comes with a sign, and so there's some restriction on what the signs can be. If you add the signs of eta and psi, they should be congruent to your parallel weight modulo 2. Okay, so this is just some restriction. Otherwise, the Eisenstein series does not exist, and for those pair of characters. So you can sort of write something down, and it doesn't make sense. Okay. Yeah, somebody said, is the paper the special values of zeta functions? So yes, this may be it. I mean, Shimura doesn't have many papers in Dukes, unlike annals. So he has many papers in annals, but I think only 2 or 3 papers in Dukes. So this may be it actually. Yeah. Okay. So to such a pair of characters, we can attach a modular form of level A times B, Neben type eta times psi, and weight K. Okay, so from now on, all our weights are parallel weights. So weight K. So that's why there's no underline anywhere here. So for each K bigger than or equal to 1, we can attach a Eisenstein series like this. And the Q expansion basically determines this Eisenstein series. So this is the Q expansion. What is the Q expansion here? So if you take the normalized Fourier coefficient at M, remember that the normalized Fourier coefficients were associated with a ideal of OF. Okay, and the lambda is chosen so that M is in class lambda. Okay, so there is no lambda for this CMF. This is for each. I mean, depends on the lambda for CMF depends on what M is. Okay, so the Mth Fourier coefficient is this thing. So these are like the divisor sums. Okay, so so these are like that we see over Q. So this is the so these are the non-constant terms, so to speak. Right, the constant term is the 0th term. These are the non-constant terms, and you can see from the form that the non-constant terms are kind of easy. Right? These are easy to understand. These are just finite sums of very good, so easy to understand rational numbers. So these are easy to understand. The most interesting terms are the constant terms. Okay, so the constant term C lambda 0, these are some L values. Okay, and I write down the list here precisely. So it's more complicated when K is equal to 1. So when weight is 1, you have a more complicated term. You have sum of 2 L values, and that's why weight 1 are sort of usually complicated also to calculate constant terms and so on. So this paper that I mentioned here, we sort of had to write it precisely because the explicit form of these constant terms at weight 1 was not, that we required was not available. This paper is kind of mainly just expository rather than, not a lot of new, I mean, not much new happens in that paper. Anyway, so so the constant terms, they depend on what the so if so there's always this term, right? If A is 1, maybe I should actually say here K is not 1 here, because if A is 1, this doesn't, there's intersection between the first and the third case, so that's not correct. So K is bigger than 2. Okay. All right. So this is just the list. I'm not going to spell it out. It's just you know explicitly what the constant terms are. Okay. So we are interested in studying L functions, and so one way into L functions is to study these Eisenstein series. Right? So that's why we require this thing. Okay. All right. So that's the example. That's the most important example of Hilbert modular forms for us. Okay. By the way, before I move to lambda-adic forms, I should have introduced a notation here. SK, just like MK, what is, yeah, K, V psi is the space of Cusp forms. Okay, this means that A lambda 0 is 0 for all lambda, and constant terms are 0 at other cusps. So I'm not introducing cusps right now, but yeah, but you saw this in for instance, Anupam's talk, where he was talking about compactification of this Y1n by attaching some cusps to it. So you can do similar things with this Hilbert modular varieties, and I don't want to go into that. But so if you haven't seen this before, all I mean is that there's no constant term when you talk about cusp forms. All right. So that was just a notation I did not introduce earlier. Now let's talk about lambda-adic forms. So you saw these lambda-adic forms in Shaunak's talk, so that's good for me. Except I'm going to do it for totally real fields. So again, sort of conceptually, maybe it's not much deeper, but notationally, it's more complicated. Okay. So Shaunak introduced these things over Q. So over Q, you can talk about power series in something like ZP or some extension of ZP, like OT or OQ, I guess is what the notation was used. And so this is because Q expansions are over Q are indexed by non-negative integers, as we just said. But over totally real fields, these are no longer indexed by non-negative integers. So I will not talk about power series like these. Okay. Right. I mean, yeah. So these are the specializations actually. So that's why, like O double bracket T double bracket Q. That's what Shaunak wrote down. And when you take specializations, you get something. So I'm not going to talk about power series in Q. Instead, I'll just take an easy way out. So so this is the thing. This is the lambda for lambda-adic forms, and for each K there's a specialization map. Okay, what is the specialization map? So this kind of thing is non-canonical. It depends on some choices, and the choice I have to make is a fixed topological generator of 1 plus PZP. Okay, this is just P. The 2 here just is relevant when P is equal to 2. Okay. So if P is equal to 2, you have to take 1 plus 4Z2. And if P is not 2, you have to take 1 plus PZP. So, so this is a topologically cyclic group. It's just isomorphic to ZP. And you fix a topological generator of this and call it U. Then there's a specialization map from lambda to OE. What does it do? It takes a power series to evaluate it at U to the K minus 1 minus 1. Okay. So for instance, in weight 0, it just evaluates it at, in weight 1, it just evaluates it's at weight 1. So nu 1 of f of t is equal to f of 0. Okay. This is kind of weight 1 is going, this K is the weight. So this is weight K specialization. So this is weight 1 is going to be the special thing for us. That's the most useful weight for us. You can see that already from this. I should have said this. So when you take E1, you get the L value at 0. Right? These are the values that we are interested in as I said yesterday in the Dirichlet class number formula. Okay, so a lambda-adic modular form is so of some level, some character, and there's no weight for this. So as you saw in Charnock's talk, so this is a collection of elements in lambda. Okay, so for each m you have Cm of f, and then for each lambda in the narrow class group you have this constant terms. Okay, and what, just like in Charnock's talk, what does this collection have to satisfy? When you specialize in weight k, you should get coefficient of a normalized coefficient of a Hilbert modular form. Okay, so for almost all k bigger than or equal to 2, these coefficients should specialize to coefficients of an actual Hilbert modular form. Okay. So just as Charnock explained in the morning, you have an infinite collection of Hilbert modular forms, and you want to interpolate them p-adically. You want to put them in one family. So this is what the lambda-adic form does. And one thing which I'm not going to explain, and I don't remember if this was explained by Charnock, is these Fourier coefficient of modular forms, a priori these are complex numbers, right? Because we defined modular forms as holomorphic functions from complex upper half plane to complex numbers. And so how do we make sense of them as p-adic numbers? And this is because they have a very strong algebricity property. So you can normalize the Fourier coefficient so that they all lie in Q bar. In a very canonical way, you can do this, and so you can think of them also as elements of QP. And this is a subtle point that I'm going to completely gloss over, because otherwise, how do I identify these p-adic numbers with complex numbers? Right? So, but something for you to keep in mind if you want to read about this. All right. So I denote the space of lambda-adic forms by this notation. Okay. Sometimes I also need to allow some of these elements to have denominators. So that's why I'll also work with M tensored with Q lambda. So Q lambda is the field of the total ring of fractions of lambda. I mean, the field of fractions of lambda. Lambda is a domain, so it's fine. Okay. So I want to allow denominators, but not too many. So I'm not saying that each of this CMF is in Q lambda, because then I have no control over how denominators grow. Okay. All right. So again, our favorite example is Eisenstein series. And again, these are the only things apart from theta series that we can write down explicitly. And I'm going to write it down explicitly. Okay, so so what this means is so you again you fix a pair of characters eta and psi of the narrow ray class group modulo A and B. Then there is a lambda-adic Eisenstein series E eta comma psi, which lies in this space. So it has level AB, it has same character eta psi. And sometimes you have to have denominators. These denominators only appear in the constant term. I'll explain that in a moment. But what is the property of this? The property is that for all k bigger than or equal to 2, we have this. Okay. For all k bigger than or equal to 2, if you take the weight k specialization, you get the weight k Eisenstein series, the usual Eisenstein series in weight k. Okay. That we wrote down earlier. So again, notice the omega to the 1 minus k here. This appears quite naturally. And this is the same thing that also appears when you interpolate the L values, right? When you take the weight k specialization of the p-adic L function associated to chi times omega, you get chi times omega to the 1 minus k. Okay, so this is the same kind of thing. Yeah. Okay. And by the way, if you're wondering about the sign condition on eta and psi, then this presence of omega takes care of the signs as well, because k is varying over all integers bigger than or equal to 2, so k is changing its parity, but the sign of omega is 1 1 1 1. Sort of, it's totally odd. So it's 1 1 1 1 modulo 2, and so this takes care of the sign. So they have the right signs. Okay. So how is this constructed? So this construction is due to Deligne-Ribet, which means the following, that so they proved its existence, but the result that they actually proved is a kind of very geometric result and not explicitly constructing this Eisenstein series. So you can write something down formally, as I'm going to write down, and Deligne-Ribet, sort of using a very heavy algebraic geometry machinery, proved that all makes sense. So they also used the result of Rappaport on constructions of Hilbert modular varieties, so, integral models for Hilbert modular varieties. All right, so how is this constructed? So again, I'm just going to write down the lambda-adic coefficients. Okay, so what is the coefficient of this Eisenstein series? Okay, these are precisely this, because of the way kind of. Okay, I skipped over this line, right? So this angled bracket norm of C, this n is norm. So this n, this n is norm of the ideal. Okay, so this is what NC is. So it's an element in ZP. If we think of it as an element in ZP. So and C is co-prime to P, so omega of C is defined, right? Omega is a character which is of conductor P, so omega C is defined, and it's also an element of ZP, because omega C takes values in mu of P minus 1 or mu of phi of 2P mu of 2 if P is equal to 2. So when you divide this norm by omega of C, we get something that lies in 1 plus P ZP. Okay, we get something that lies in 1 plus p zp. So this is the notation, angled bracket norm of C. So if you copy the formula for the Mth coefficient of this Eisenstein series from a few slides above, and compare it with this, it's exactly this, because it's norm of C, but you have omega to the 1 minus k here and omega to the k minus 1 here. Right? So yeah, so you these things match. Okay. Now these are, as I said earlier, these are kind of the easy terms, and you can periodically interpolate them. Okay. So so these terms can be periodically interpolated. Okay, and why is that? This is because they satisfy the congruence that you want it to satisfy. Okay, so if you want to interpolate something periodically, what does this mean? It means that this interpolated periodically as a function of k, right? As a function of k. So what does continuity mean? It means that if k and k prime are close together, then these quantities are also close together. Right? These are periodically. So it means that if k and k prime are congruent modulo some high power of p, and you have to have this p minus 1 here, just as in Kumar congruences. I'm not going to try to explain this here, but yesterday we saw this in Kumar congruences as well. So if k and k prime are periodically close, then these quantities are also periodically close. And so what is the thing that's varying with k? It's this norm term. And you can see that if you take any integer to the power k minus 1 and the same integer to the power k prime minus 1, they'll also be periodically close. So this is yeah, you apply Fermat's little theorem and then keep taking pth powers, and that's how you prove this congruence. Okay, so this is really elementary. So you show that at least the non-constant terms can be periodically interpolated. Okay, so this congruence implies that there exists an element in lambda such that weight k specialization is precisely this term. Okay. So the upshot of all this is non-constant terms can be periodically interpolated. Okay. All right. So what about the constant terms? As I said earlier, the constant term is the most difficult one because it's an L value. And how do you say anything about it? So whatever I did up to now it's not hard at all. It just uses Fermat's little theorem. So that couldn't be the part that Deligne-Ribet had to figure out. So the part that Deligne-Ribet had to prove was this Q expansion principle. Okay, so this is the difficult thing. So what does the Q expansion principle say? Sort of very roughly, it says that if you take the Q expansion determines the modular form. This is what it says. So you saw, I think Shaunak mentioned the statement that the Q expansion, the Fourier coefficients that determine the modular form. And I mean, so I'm kind of putting a lot of like the Hilbert modular varieties theory under the rug, but yeah, so at least the moduli space that Deligne-Ribet can consider in that situation, the Q expansion map is injective. Okay, so the Q expansion determines the modular form. This is one form of the Q expansion principle, but alternately you can write it like this. So if you know that the non-constant terms, if you know that these non-constant terms are integral, okay, if you know that non-constant terms of the Q expansion are integral, then you would like to say that the constant term is integral. Well, that's not quite true. what is true is that if you take the constant term at two different cusps, okay, so if you we always up to now we always looked at cusp at infinity, but there are other cusps, and so you can look at Q expansion at those cusps. And if you look at the constant term at the different cusp, then the difference between these two constant terms will be integral. Okay, so this is the precise statement of the Q expansion principle that we need. And what the so in particular, if the constant term at some other cusp is 0, you can say that the constant term at infinity is integral. Right? You can say so, you get some statement like that. In any case, so you just have to calculate constant terms at a different cusp and then take their difference, and this is what it precisely spits out this p-adic L function. Okay, so so these usual Eisenstein series that was not that did not have the Euler factors at S removed, right? We are removing Euler factors at S here, as we saw yesterday. These did not have the Euler factors at S removed, but when you take this difference between two constant terms, right? Constant term at infinity and constant term at another cusp, the effect that it has is precisely sort of removing the constant terms. Okay, so what you get is a p-adic L function as the constant term. So yeah, I mean, okay, yeah. So yeah, I don't want to sort of go in. I mean, this would be a course in itself if I did go into it. So the reference for this is the paper of Delin Rebet. Values of abelian L functions at negative integers, I think it's called. Values of abelian L functions. Yeah, it's in Inventionness, so should be very easy to find. Anyway, so you can read about the construction, but the basic thing that it uses is this Q expansion principle. And the proof of this Q expansion principle is some geometric result that yeah, so Vansu asked if why should we take difference between two constant terms? So and in practice, do we have cusp where the constant term is 0? So yes, often we have cusps where the constant term is 0, or another way of making a constant term 0 at some cusp is by taking some kind of stabilization. Okay, so this is actually what one usually does for this construction, but so that's one way of making constant term 0 at some cusp. And the reason why, so this is this I suppose is a statement that's kind of believable if you if you know that the moduli space is reducible, right? So if you know that the moduli space, irreducible, if the moduli space is irreducible, then you can believe something like if a form is 0 in a neighborhood of some cusp, then it's going to be 0 everywhere. And the reason why we have to take difference of for the second statement, the reason why you have to take difference at two distinct cusps is the lambda-adic cusp, the lambda-adic forms, they don't come with weight. So you can take your lambda-adic form that you have for the statement, and then you can take the constant lambda-adic form. Okay, so like constant functions. So constant lambda-adic form, which is the constant term at different cusp, and then you take their difference. So what that is doing somehow is kind of yeah, and then you use the first statement. So you can look at Deligne-Ribet. They explain how this implies this, but that's how you yeah, by taking the difference, you get something which is whose constant term vanishes at a different cusp. Okay, and is that thing some kind of generalization of, I don't know which thing, the taking the difference between yeah, sorry, I don't understand the question. It says, is that thing some kind of generalizations of Atkin-Lerner theory? There is a generalization of Atkin-Lerner theory to Hilbert modular forms. Oh, if you mean that by that thing, no, but it's more like the stabilization. So Q expansion injection. Yeah, I've no, it's just it's always called Q expansion principle. So yeah, I don't know any direct relation between Q expansion principle and Atkin-Lerner theory. Okay, so this is my sketch of construction of p-adical function. Okay, this is how Deligne-Ribet construct p-adical function. The construction given by Castelnuovo is completely different. It uses these explicit formulae that Shintani gave for partial zeta functions. Okay, and the reason why I recalled this lambda-adic thing in such detail, even though very hastily, is because we are going to use these Eisenstein series explicitly later on. Okay, and the only thing we need to know is what the constant terms are and what the Q expansion is, and so on. Not much more than that. So that's why I wanted to give this example in somewhat of a detail, but I can't sort of give all the details. Okay, so now we come to our main topic, the Gross-Stark conjecture. So now it's sort of, we again change track completely. So this theory of modular forms, that section is done. Now we look at we come back to our L functions and the Gross-Stark conjecture. Okay, so so recall that that we had this finite set S containing all primes above P. So recall that we had our I think I write this somewhere else, but so we had our F, and then we had some character which kind of yeah. So S is a finite set of places of F which contains all primes above P, and we had this this p-adical function that interpolated this this S depleted L value. Okay, so this is a term that's used sometimes, S depleted. So you're depleting the Euler factors at primes in S. So as I said yesterday, when you evaluate it at 0, you have to multiply it by this product. Okay. Now, if chi of V is 1 for some V in S, then you get that the value of the p-adical function at S equal to 0 is 0. Okay. Now, what happens when V is not above P? When V is not above P and chi of V is 1, there is a relation. I mean, then you can also define a p-adical function without this V in the set. Okay. So, and yeah, without this V in the set, and there's a simple relationship between these two p-adical functions. So this has V in S and this does not have V in S, and there is a simple relation. So we haven't removed Euler factor at V in this p-adical function, so we just remove it, and this is a p-adic function. Okay, so this is a p-adic function. Right, because right, so all this means is this same congruence that we wrote down earlier. So K is congruent to K prime, mod P to the T P minus 1 implies norm of V to the K is congruent to norm of V to the K prime modulo P to the T plus 1. Okay, so So this holds, and this is because, so since P does not divide norm of V, that's the reason. If P did divide norm of V, we wouldn't have this congruence. So that's why if V is a place above P, we don't have a p-adic version of the Euler factor. Okay, so if V is not above P, we just have to multiply it by this factor. And when you let S go to 0 p-adically, we get log of norm of V. Okay, so this is the p-adic log of norm of V. So that's why the L the L function here is related to the L function here in this way. Sorry, I should say yeah, this is the I mean this is I should say this is the leading term. So the leading terms are related by this simple factor, p-adic log of norm of V. Okay, p-adic log is just something that's defined by the usual power series expansion on 1 plus pzp. You extend it to qp by I mean log of roots of unity is 0 and log of p is 0. So that's how you extend it to qp cross. So this is Iwasawa's p-adic log. We'll see this again. This log is used quite a lot. All right, so so that's the story when V is not above P. So very easy. But now if V is above P, we cannot do this anymore. Okay, so this does not work if V is above P. So what happens when V is above P? The story is much deeper, and that's what I'm going to tell you now. So let R be, so from now on, S is precisely the set of no, so yeah, but Bharat asked if Kubota Leopold have a construction of p-adic L functions using Stickelberger element. Is there an analog for this Delin-Rebet-Castelnuogas p-adic L function? And the answer is no. In fact, it kind of goes the other way around. You construct the p-adic L function, and then you know that the Stickelberger element has the integrality properties that you want it to have. And not, yeah. So the story is in fact it goes the other way around for general totally real fields. Okay, so the projection of these integral elements, that is what you call Stickelberger element in this for totally real fields. There's no explicit expression for Stickelberger elements like there is over Q with Bernoulli numbers or such things. You know, like fractional part of A over M and so on, this kind of thing. All right, so I take S to be the minimal set that I want. Okay, the minimal set that I can. So I just take S to be all the places above P, because if I have places which are not above P, then I know how to take care of them. And R is the set of all places above P for which chi of V is not 1. Okay, it could be 0. Chi of V could be 0 if V is ramified. I don't care about that. But I just put them in R. And R1 is all the places above P for which chi of V is exactly 1. Okay, and my R, small r, is the number of elements in R1. Right, and because my S is this minimal set, from now on I'll just denote LSP by LP, just to ease the notation. Okay, so if R, small r, is bigger than or equal to 1, which means that there is at least one V in S such that chi of V is 1, then I know that the p-adic L function is 0 at 0. So this is kind of easy, but you can ask like, what is the order of that 0? And this is in fact a very hard question. So this is the first conjecture that Gross made, which is that if the number of primes above P for which chi of v is 1 is exactly r, this integer r, then the order of vanishing of the p-adic L function at s equal to 0 is precisely r. Okay. I should also say here, okay, for r equal to 0. So when r is equal to 0, this is kind of obvious. So this is known, okay, for r equal to 0, this conjecture. And even for r equal to 1, to say that it has 0 of exact order 1 is a very hard question. So you need to use Baker-Brummer theorem for this. So there's a theorem of Baker which says that if logs of algebraic numbers are linearly independent over Q, then they are also linearly independent over Q bar. Okay. Or another way of saying this is if logs of algebraic numbers are linearly dependent over Q bar, then they are already linearly dependent over Q. So, so this is a very famous theorem of Baker, for which he got Fields Medal. And Brummer proved a p-adic analog of this by essentially the same method. And this is what you need to prove Gross's conjecture for r equal to 1. I'll say in a moment why I put name of Kuzmin here. But this is basically Gross's conjecture. But beyond r equal to 0 and r equal to 1, this conjecture is kind of completely open. We don't know how to show that the order of vanishing of this p-adic L function at s equal to 0 is precisely r. Okay, and I think it's a really difficult transcendental number theory problem, p-adic transcendence theory problem. For instance, it follows from Chanuel's conjecture, okay, which is a sort of very difficult problem. But what is known is that the order of vanishing is at least r. Right, so when r is 1, we know that the order of vanishing is at least 1 without using Baker-Brummer. But that is kind of trivial. That is trivially true. But when r is bigger than 1, proving this result is also not easy. Okay, so there are two proofs of this. One is due to Wiles. What this means is that Wiles proved the main conjecture. So this p-adic L function is equal to, up to unit, it's equal to some characteristic element. And then you can show that the order of vanishing of the characteristic element is at least r. So that's how you use Wiles as a result to prove this. And there may be some issue at p equal to 2 in applying Wiles. I'm not sure about, somebody mentioned this to me, but I did not try to do p equal to 2. But there's a completely p-adic analytic proof due to Charlois, Dasgupta, and Matthew Greenberg, using their Eisenstein co-cycles. So this in fact uses a Shintani kind of method. Okay. So in some sense, they use Shintani's work here, Casanoga, Shintani, and so on. So this is a completely p-adic analytic proof to show that the order of vanishing is at least r, and they also and it works uniformly whether p is 2 or odd. So no, I mean, so Bharat asked whose work proves r equal to 1 case in totally real case. No, this is, I mean, this follows from Baker-Brummer, and that's noted in two different papers. One is, I think it's also in Greenberg, some paper of Greenberg where he says r equal to 1 of this follows from Baker-Brummer. And there's a paper by Gross and Federer and Gross, Leslie Federer and Gross, where they kind of note that r equal to 1 case follows from Baker-Brummer. For Q, I mean, yeah, I mean, Ferrero-Greenberg is somewhat more refined than this. I mean, they have some gamma function values there, I guess. Yeah, I forget the precise statement of Ferrero routine. Yeah, this is related. Okay. All right, so that's the first conjecture, and Kuzmin made a conjecture on. So this is analytic side. Kuzmin made a conjecture completely on algebraic side, and it turns out that those two conjectures are equivalent. So that's why I put Kuzmin's name here. Okay. Now there's a second conjecture that Gross made. So first he said that the order of vanishing is R, exactly R, and then he said that the leading term has a particular expression. Okay, so but I'll not write it as a leading term. I'll write it as Rth derivative. Okay, so Gross conjectured that Rth derivative of this p-adic L function at s equal to 0 is, well, you have the oops. You have R factorial because you're taking Rth derivative. So this is, I suppose, very natural. And you don't have the S depleted L value anymore, but only R depleted L value. Okay. So R, remember, was all places above P for which chi of that place is not 1. So you still have to remove those places. So you have your relationship with complex L value back, right? The thing that you lost when there was trivial 0. Now you see that L value in the Rth derivative. So that's your redemption. But there's this complicated factor which is called the Gross regulator. Okay. So Rp chi, and I'll denote Rp chi next. So this is the Gross regulator. Okay. So I want to make some comments about this. So the reason why I write Rth derivative and not the leading term is because that makes this this statement independent of conjecture 1. Okay. So Rth derivative could be 0. I don't care if the order of if this conjecture fails, and I know that the order of vanishing is at least R, then and if the conjecture fails, then the order of vanishing is bigger than R. So Rth derivative will be 0, which means I have to show that this side is also 0. So there's still some non-trivial content in the statement, even if conjecture 1 fails. Right? If conjecture 1 is true, then by using this equality, I know that this side is non-zero. And if conjecture 1 fails, then I know that this side is 0, and I have to show that this side is 0. So that's what we prove. Okay, so if conjecture 1 is true, then we prove the equality. If conjecture 1 is false, then we prove the equality by proving that both sides are 0. So that's one comment. The other is, so this was proven for R equal to 1 by Dasgupta, Dharma, and Pollock, with some assumptions that were removed by Ventulo. And then the general case was proven by Dasgupta, Ventulo, and myself later. Okay, so this is what we are going to see a proof of. All right, so I'll try to give you the definition of this gross regulator in the remaining few minutes that I have, and then we can continue next time. So I want to define this gross regulator. Okay. And I defined the Dirichlet regulator last time, and this is very similar, except that this is all happening at p-adic places rather than real places. And so the object that I'm interested in is this. Yeah, now I realize that. Oh no, sorry. Yeah, I'm fine because I took minus. So, right. So this is the p units in U is the p units in H. Right. Remember, I had this diagram above as well. H is a extension of F cut out by chi. U is p units in H. X is the free abelian group generated by p-adic places of H. Okay, so SPH. These are places of H above P. Okay? So not above. So this is different from S. S was the places. S was the set of places of F. These are places of H which are above S. All right. U minus is all elements, all P units. So C is complex conjugation. C is complex conjugation. Remember that chi is totally odd. Okay, chi is totally odd. So complex conjugation is a well-defined element of G. Okay. So I want all the, these are called anti-units, right? So these things are called anti-units sometimes. Yeah, actually, I don't want to say this because yeah. You have to say something at Archimedean places as well. So let me not use that term, but these are all units so that complex conjugation acts as -1. Complex conjugation also acts on X because it acts on all places of H above P, and I can take X minus, which are all elements in X, on which complex conjugation again acts as -1. Okay, and E is just some sufficiently large extension of QP. Then there are two G module maps from E tensored U minus to E tensored X minus. So taking minus part of Z modules is a tricky thing because, you know, whether do you take quotients or do you take subs, and the two things are different in general. But I'm going to tensor everything by a field. So whatever definition I take after tensoring, you get the same thing. So that's why I don't care, and I just take the sub. So there are two maps from E tensored U minus to E tensored X minus. And what are the two maps? First is called OP. What does it do? It takes an element in U minus and it sends it to, maybe because I said free abelian group generated by places, I could write it like this as well. But this is just a matter of which notation you prefer. Right? So this is defined on U minus, and then you just extend it E linearly when you tensor. So these tensors are over Z. When you don't write anything, I usually mean Z. So OP of X is you take odd P of X at each place P, and LP you take norm of, sorry, this should be X. Okay. So to define LP, you take norm from HP to QP. So X is an element in HP because it's an element in U minus. You can take norm all the way down to QP, and then you take the p-adic log, this Iwasawa's p-adic log of that. Okay, so that's the, and this minus sign is just some normalization that I like to use. So there are these two maps. Okay. Now, what do I know about these two maps? Well, Dirichlet's unit theorem. So it's not just about OH cross, right? Dirichlet's unit theorem is not just about OH cross. It also applies to OH1 over S for some S, right? So, or maybe I should write sigma here, something like this. So it also applies to, throwing away, throwing in more like P units and so on. So Dirichlet's unit theorem, in fact, tells you that this OP is an isomorphism. Okay. And conjecturally, LP is also an isomorphism. But this is the first conjecture. This is equivalent to the first conjecture of Gross. Right? This is after the theorem that we proved. But this is also conjecturally, this is also an isomorphism. So this is the transcendental problem that I was talking about. So let me just take a couple of minutes more than my time. So conjecturally, LP is also an isomorphism, but we don't know this conjecture, and so we sort of don't consider it. Now I can take chi parts of the this map, right? This is all characteristic zero, so taking chi part is easy. you take all elements in these things on which chi acts by chi inverse of sigma. Sorry, this chi, I mean, though I say chi part, I have to put chi inverse here. This is just some, again, matter of convention rather than anything else, but this is consistent with our paper, so that's why I'm using this notation. Okay, so I can take chi parts of these maps. So that goes from chi part of E tensored U minus to chi part of E tensored X minus. Okay, now I can take O inverse in this direction and L. So like this, and compose them. So I get a map from X to X itself, right? So I can go this way. This is what this map is. And because it's a map from X to X itself, I can take its determinant. Right? I can, I can fix any basis and then take its determinant. So that's a well-defined element of E. So this is the Gross regulator. This is the definition of Gross regulator. Okay. So I think I wanted to do the reformulation of the Gross-Stark conjecture in terms of some cohomology, existence of some cohomology classes, but that will have to be postponed to the next talk. So yeah, so that's the definition of Gross regulator, and this is the statement again. I'm just recalling it here. Okay, I already said this remark orally. So conjecture 1, because of the statement that we prove, means that conjecture 1 is equivalent to this p-adic regulator being non-zero. Okay, so this p-adic regulator being non-zero, this is a different conjecture than a Leopold conjecture, but it's very similar in, yeah, somebody just wrote. Is there some analogy with conjecture 1 with Leopold conjecture? Yeah, so that's exactly what I was going to say, Anupam, that Leopold conjecture is about Leopold regulator, which is p-adic logs of actual global units. This is about p-adic log of p units, but it's the same kind of transcendental number theory question. So for instance, both are implied by Chanel's conjecture. So the nature of the Leopold conjecture and conjecture 1 is very similar. By the way, another comment I could make in this regards is so somehow there's also like, yeah, Leopold conjecture is about non-vanishing of a Leopold regulator, but one often states it as the p-adic zeta function having a pole at s equal to 1, and this is what I did in my last lecture. But to get that equivalence, one has to use a result of Kolmez about Kolmez computed residue at s equal to 1 of p-adic zeta functions. And you have to, so that's some kind of analog of this result at s equal to 1. P-adic L functions don't have a functional equation relating s to 1 minus s. So you can't deduce this result from that and that result from this. In fact, I mean, though Kolmez's result is much older, kind of seems to me a little bit deeper than what we do. Though it's only for zeta functions, whereas this applies to all functions. Yeah, so yes, there is indeed analogy with Leopold's conjecture. Okay, I think I should stop here. Sorry for going over.
Okay, so thank you very much, Professor Mahesh Kakde. So are there any questions, comments? So there is a recent message in the chat box. Mahesh, can you read it out? So how did such an idea of the maps OP and LP come up? So
well, I mean, yes. So the idea for the map OP is kind of there in Dirichlet's unit theorem, right? That's what I said. Usually you take like usually, I mean, like the way it's written in the usual V for Dirichlet's unit theorem is some kind of like log of yeah, like log of norm of something. What do I want to say? Yeah, the usual log, I mean, log of norm of something. So, so this is the usual log. And when you take the usual log, you kind of get odd of, so this is like odd of, sorry, let me, so, this is like some multiple of ord of v, some multiple of ord of v times log of p. So p is the residue characteristic of this thing. So there's this simple factor log of p that comes out. So so we just ignore that and work with ord of p. Sorry, I'm not so sure about this expression, so I'm going to erase this from here. So that's the usual thing that's taken in Dirichlet's unit theorem. So that's the idea for taking this OP. And then you can't really take I mean, you need another way of identifying U and X. Right? And so this is what Gross figured out, that there's another map which is taking p-adic log instead of the usual Archimedean log that I just wrote here. Okay, so if you look at that Archimedean log and you know there is a p-adic log, so you can try to take that. So I think that's why it's maybe kind of natural to look at these two maps. Otherwise, you can't define a defined determinant if you have a determinant is not a well-defined quantity. If you just have a linear map between two distinct spaces, you have to fix a basis somehow, and so either you give a way of fixing a basis or you define a map in the other direction. So that's what Gross did. And what do you mean by the embedding? The embeddings, I'm not sure. Okay, there's someone else who's raised their hand.
Yeah.
Yeah, I don't know if they can.
Yeah. Do you hear me now?
Yes, please carry on. Yeah.
In fact, I think all of you said have analytic taste, and you said that Kuzmin made a conjecture with algebraic taste that is equivalent to the Gross conjecture. What is the Kuzmin conjecture, in fact?
Yeah, so one way to state this is you take the cyclotomic ZP extension of a totally real. No, sorry. So okay, here's a way to state this. So you take the so you take the cyclotomic ZP extension of this extension H. Okay.
Yeah.
And you take the maximal abelian P extension of that of H cyclotomic. So cyclotomic ZP extension. You take the maximal abelian P extension of H cyclotomic, in which all primes above P split completely.
Oh.
Okay. So Kuzmin conjecture says that extension is a finite extension of H cyclotomic.
Oh,
okay.
So it is related to Iwasawa's theory.
Yes, so that's that is a way to I think that's the way Kuzmin stated it.
And it's amazing that it is equivalent to this conjecture. And how prove that the Kuzmin conjecture and Gross conjecture are the same?
Oh yeah, to prove that, you basically you have to use the main conjecture to prove that they are the same, because main conjecture because Kuzmin's conjecture is kind of directly equivalent to saying that the characteristic power series, whatever you take, a generator of the characteristic ideal has order of vanishing precisely R at weight 1. I mean, that relevant point at s equal to 0, if you like, if you write it in this way. And then the main conjecture says that p-adic function is a generator of characteristic ideal, so that will also have order of vanishing exactly R. Yeah, so you have to go through main conjecture. It's not.
Oh, very, very nice. Thank you. Very nice.
Okay, so it seems there are no more questions or comments. So let's thank Professor Mahesh Kakde again.